So for our next thing we'll think about, what if we take our long rod and we bend it into a ring? What if we make a circle out of it? So let's say we have a thin ring. The ring has a radius A, so from here to here has a distance A. It has a total charge Q, which is uniformly distributed over the length of the ring. Find the electric field at some point X along the axis of the ring. So the axis of the ring goes right through the center and it's perpendicular to the plane of the ring. In terms of the coordinate system, we also have a y-axis that points straight up. So our y goes up and down, and z comes out of the page. Negative z goes into the page like this. Okay, so there's our coordinate system. And we're trying to find the electric field at some point P right here. So what is the electric field at this position? We're going to follow our steps exactly the same as what we did for the long rod. The first thing we do is we pick some value of dq. We identify a small piece of the ring which has a small amount of charge, and we call that small amount of charge dq. Where do we pick our dq? Well, we don't want it at a point where there's kind of an extreme. So we don't want it right on top of where the axis meets y, where it's at z, or where it's at x. We want it somewhere off to one side a bit. I'm going to pick over here. So I choose a little bit of the ring. That little bit of ring has an amount of charge that I call dq. I want to draw the electric field vector at point P due to this amount of charge dq. So I know I'm going to need that distance. Here's where life gets a little bit tricky. It's hard to sort out which way this dE points, especially if we're looking at a two-dimensional drawing on paper. We've got two-dimensional paper for a three-dimensional object. So I am a fan of props, so what I grabbed, and I had to grab what I had at home, was a roll of masking tape. So this is our ring of charge, and this is going to represent the electric field vector. So the distance r drawn in the picture here, that's the length of my lollipop stick, and my little bit of electric field dE is my arrow right here. So this is my ring. I'm going to hold it up the way this ring is supposed to be. So one end is coming out towards you, one end is going away. My x-axis is coming through the center. And I've picked a piece of my ring, dq, to be kind of off one side a bit. So now I'll ask, what does the electric field do? Well, I know it points away, and I want it at some point along that axis. So I know it points away, so I put this end of my lollipop stick at dq, and I'll put this end at my point P, so this end goes at point P. And what I see that it does is it points in this direction. It's hard to describe exactly how it points. It points down in towards the page, it points down towards the bottom of the page, and it points towards the right of the page. So into the page, bottom of page, and right of page is the way that it points. Okay, I'll move it now and maybe you can see it a little bit. So kind of like this. So now I'm going to try and draw it. So my electric field vector points away from that little bit of charge dq. So there is the little bit of electric field. Little bit of electric field is called dE, and it points away from that little bit of charge dq because my ring has positive charge. This dE has components, so the x component points towards the right. There's my dEx. My y component points down towards the bottom of the page, dEy. And my z component points out of the page towards us, dEz. And this is why we chose the part not on where the ring meets one particular axis, because we wanted to see all three components of our electric field. We wanted all three components of dE. Okay, so we've drawn our dq, we've drawn our dE, we identified our components. Next, let's write down how big is our dE. So what's the magnitude of dE? The magnitude of dE, the size of dE, comes from our expression for the size of the electric field. We know that around a point charge, E is kq over r squared. So around that little point charge, and dq is like a point charge because it's very small, it's k times dq over r squared with the direction as we drew right here. We need to start thinking about what we're going to plug in here for dq. What are we going to plug in for r? But let's sort out the symmetry first. Does anything cancel? If we sort out some symmetry, then we might not have to do quite as much work. The symmetry can be hard to see. I recommend you go grab a roll of masking tape and use a couple of pencils or pens and try and model what I'm doing here to see if you can see the cancellation. Okay, so first things first, ask yourself, can I see what cancels? Do I know what cancels? If you don't know, that's fine. I would imagine you're in very good company. A lot of people wouldn't know. So here's my ring. It comes out of the page like this. I'm going to lay it flat for right now. Because maybe it'll be a little bit easier to see those arrows. And now what I'm going to do is I'm going to say that this is a point dq. So from that dq, I know the electric field is going to come point straight out, so it comes like this. Now I'm going to ask, if I look at the identical point on the other side, what cancels? So I pick an identical point on the other side, and what I see is the components that are left and right, and up and down. So the components this way and the components this way, they cancel. But the components that head straight out of the page, they don't cancel. And that's true no matter which 2 points I pick. Okay, so our x-axis is out of the page at us, y-axis is this way, and z-axis is this way. So no matter which way I turn, the y and z components cancel, and the x components don't cancel. If you wanted to think about it in terms of this picture, every dq from the top half of the ring makes an electric field that points down. Every dq from the bottom half of the ring makes a dE that points up. So the y components from this half point up, the y components from this half point down, so all those y components will cancel. The back half of the ring have z components that point out of the page towards you. The front half of the ring has z components that point into the page away from you, so those z components cancel. The x components, no matter where you are on the ring, your x components always point to the right, so they never cancel. Okay, hopefully that clarifies it a bit. So again, just like the long rod of charge, it's not that dEy is 0, because it clearly isn't. Our dEy and our dEz's are not 0, but the sum of them, the integral, that is 0, because when we add them all up, that becomes 0. So Ey, which is the integral of dEy, equals 0, and Ez equals the integral of dEz, that equals 0. And the reason that's true is from the symmetry. I would suggest as an exercise that maybe you go ahead and try and calculate that for yourself. Do you see that that works out to be true if you go through the math process? That could be an interesting exercise for you. Okay, so our y and z, and you don't have to. If this were a test, it's enough to say by symmetry. It's okay to recognize that. It contains a lot of physics to know that it's 0 from symmetry. But if you just don't buy it, then by all means go through the math and see if you can sort it out. So now let's get to our x component. So Ex is going to be the integral of dEx. What do we mean by dEx? Well, here's our dEx. Here's our dE. I'm going to call this angle theta, which makes this angle theta. So my dEx is adjacent to my angle, so dEx is dE times cosine theta. Okay, let's sort out what I can fill in here. I know right off the bat that dE is k times dq over r squared. What's cosine theta? What's dq? What's r squared? What are our variables and what are our constants? Okay, those are all the questions we're thinking about as we set up our integral. Let's deal with cosine theta first. So cosine theta is adjacent over hypotenuse, and that's where we get our dx on this side of the triangle. On this side, our adjacent is the distance from the center of the ring to point P. That's our distance x. This side of the triangle is the distance a, and this side of the triangle is distance r. So cosine theta is adjacent over hypotenuse is x over r. Let's put that in up here. I'm taking this step by step rather than finding everything at once. Doesn't really matter which way you do it so long as it makes sense to you. So k times dq over r squared times cosine theta, which is x over r. Got r squared here, r here, that brings us to r cubed. Next, let's sort out r. Well, r is the hypotenuse of a right angle triangle where the two legs are x and a. So r is equal to the square root of a squared plus x squared, which we can write as a squared plus x squared to the 1/2. I can fill that in up here. I've got r cubed here, so I'm going to cube this expression, which is going to give me a squared plus x squared to the 3/2. Next, I'm going to ask what's constant and what's variable. A is the radius of the ring, constant. X is the distance between the center and point P, constant. R is our distance this way, constant. Theta is our angle. Remember, theta could be found as the inverse cos of x over r. Theta is constant. So A and x and k are all constants. They can come outside the integral. So now what I've got is the expression, the integral of dq. What does the integral of dq give us? What does it even mean? The integral of dq means we add up all the small bits of charge as we go around the ring. So if I add up every single little bit of charge going the complete way around the ring, what I would get for my answer would be the total charge. And that's the fundamental meaning of an integral. So my answer for the magnitude of the electric field is k times q times x over a squared plus x squared to the 3/2. So there's the size of my x component. Now I need to finish and write down my electric field as a vector. I said that my x and my z and y components would cancel. I'd only have my x component in the end. So my electric field vector will not have a y or z component. This will be our x component. And the direction is I hat, or to the right, and that's because the ring is positively charged, points away. If it were negative, it would point inwards. For some homework questions, I'll post solutions. Maybe I'll do a video, maybe not. What is the field at the center of the ring? So what happens if x equals 0? Where is the field a maximum and how big is it? And what is the field if we're very far away? Okay, so there's some things you can try for a homework project.